Hi, everyone. My name is Gina, and I'm a product manager at Warby Parker, and I own the core frame shopping funnel on the website. And today I'm going to talk to everyone about the common mistakes when starting A/B testing. First, I definitely want to get into the context as to why I wanted to talk about this and focus on this. So I really wanted to focus on this topic because when I first started as a PM, A/B testing intricacies was both the more challenging concept to grasp and the most fascinating to me. And once I started to conduct more A/B tests, I wanted to know more about them, such as the foundations they're built on, and also how I can be conducting them better. But one does not simply become a data scientist. So I learned mainly from launching different experiments that ranged in complexity and partnering with data scientists to understand concepts more. So I really hope what you can gain from this presentation is that although A/B testing frameworks can be intimidating, there are ways to gain a lot of insight from them, and it can be one of the more fun parts of where data science and product management intersect. So I'm going to ask a big question here and really start from the beginning. Why, what, and how do we A/B test? So we're going to get a bit into this. So touching on the what. So A/B testing is also known as split testing and is a process of showing two variants. So variance is a term you use within A/B testing, but it really is referring to versions of the same web page to different segments of website visitors at the same time. And you're comparing which variant drives more conversions. So as you can see here, the old experience is normally referred to as the control variant. The new experience we're going to say is called the enabled variant, but it's essentially a new experience. And with A/B testing, you don't always have to do a 50-50 split. You can have the control experience, the old experience, and then two new experiences, which that would be ABC. You can also have three new experiences you want to test against the control. So that would be an ABCD. The one caveat is the more variants you add here, the more traffic and the more power your experiment needs in order for you to get the data you need to learn from it. So getting into the why. Why do we A/B test? So we test to measure the impact of changes or features we introduce to a digital product. The goals of the changes you're looking to make usually fall into two buckets. So as a product manager, you're looking to solve user problems, but then you also could be wanting to make low risk modifications. And the most common impact you're trying to measure is impact on conversion, so driving more dollars, and then also user behavior. So you might have a goal of just having higher engagement and a lower bounce rate with the feature or the modification you're launching. Some examples of what a larger feature would be that you want to test could be redesigning your website, changing your pricing structure. That's not even a feature, that would be just you changing a specific structure on your site that you want to make sure you're not driving a negative with. And then some smaller changes which would be considered like a low risk modification, would be changing copy, say like on a product detail page. So you want to try to optimize the copy there and make sure it's not driving a negative. And if anything, either it's neutral compared to the old version or it's driving positive. So getting to the how here. So how do we A/B test? So A/B testing is built off of statistical hypothesis testing. And this is an assumption about a population parameter. And this assumption may or may not be true. So statistical analysis is our best tool for predicting outcomes we don't know using information we do know. And what hypothesis testing uses as a concept is called the null hypothesis, which proposes that there's no difference between certain characteristics of a population. The null hypothesis is really the devil's advocate of the experiment. As a product manager, you're probably used to being the devil's advocate in the meeting room, but it's essentially saying, what are the chances of you seeing this effect if you were just to run the current experience against itself? What are the chances that this is just chance and it's not an actual effect? So it's also asking how much background noise is there and that the effect, and really is the effect you're seeing random. So when we A/B test, ultimately we are measuring if an observed difference is statistically significant. when we run experiments, we're looking for statistical significance. What statistical significance does for us, it allows you to reject the null hypothesis. So that devil's advocate allows you to reject it and say that the effect you're seeing is not due by chance. Whether that effect is positive or negative, it's not due by chance. So reaching statistical significance in general is what you look for as a product manager. So another big question here, what does statistical hypothesis testing look like in practice? So we're going to launch an A/B experiment together. So let's say we're launching an A/B experiment that is introducing a new filtering UI on our make-believe website. First and foremost, we're going to want to have an experiment design and list out our problem statement. So why are we testing? What change are we testing? The goal, how are we measuring this? And the duration. So let's dive into these a bit more. So why are we testing? Our user problem is users have friction when using the current filtering experience. It's not clear to users when they have an option selected. So that's really the friction point that we know from our data, that users are having confusion around this and they don't understand this. So getting into what change are we testing? The control, which would be the current experience, is 50%, and they're going to be seeing this current filtering UI. So the current UI that has friction. And then the enabled would be 50%, user sees updated filtering UI. So ideally, we're going to be solving the user problem of a user not understanding when something's selected within the new version. Then how are we measuring? So our primary metrics for this are going to be on-site conversion rate. We care about driving more dollars with this updated UI. And secondary, we have here add to cart rate. Now, add to cart rate could be your primary metric. It's really based off of what your ultimate goal is with the feature you're introducing. Add to cart rate's a good metric to have to understand the health of your feature. It doesn't always totally correlate with on-site conversion, but it can help you to understand if you're promoting the purchasing behavior you want from users and give you a better assessment on that. And then the duration. How long are we running it? So we're running it for 2 weeks. It's worth noting how you would calculate this. If you search sample calculator on Google, you can find a calculator in order to figure out how long you want to run experiments. But in general, what this sample calculator is going to ask you is the conversion of the site area you want to test on, how much traffic does that site area usually get? And it'll also ask you how many variants are going to be included. So are you going to have 2 variants? Are you going to have 3? And then it will let you know, based on this, how long you should run your experiment. It's also important to upfront list out your decision criteria for the experiment. So this is going to be our decision criteria for this new filtering UI. If results are positive, we will choose the enabled variant. If results are neutral, we will launch the enabled variant since it has a slightly updated design. And then if results are negative, we will revert back to the control experience and evaluate what drove the negative and iterate. So you might be asking, how will we be measuring statistical significance in this experiment? And so we're going to touch on p-value based cutoffs. Now I have a disclaimer here about p-values. They are a very complex concept, and I could have just a full talk on this concept. I plan to speak to them more at a high level and how they're typically used in feature experimentation. So in conducting an A/B experiment, the most common way to read statistical significance is through p-values. So the most common p-value used is 0.05, so 95% confidence. And if your p-value falls below this, it's deemed as statistically significant. In other words, there's less than a 5% chance that the effect you would also see if you were to run an AA test and it's not due by chance. So remember that devil's advocate, the null hypothesis. What this is saying is if your p-value falls below 0.05%, you're able to reject that null hypothesis and say it's not due by chance, it's an actual effect. That's unique. So really what p-values communicate is a categorical cutoff of statistical significance. So is the effect size statistically significant, or is it not statistically significant and above 0.05, the p-value? So let's say, another big question, let's say your experiment is not statistically significant, determined by the p-value. Now what? So most PMs generally stop here, but what a categorical cutoff value such as a p-value doesn't tell you is the magnitude or the importance of the effect you see. So in other words, should I care about this effect regardless if it's statistically significant? So let's say we ran our experiment for 2 weeks, and these are the results we got. So our control, let's concentrate on the column all the way to the left, the sales conversion. So we can see the control has a 3.34% conversion. Enabled is 3.36%. You can see the lift here is 0.02%. Now, if I was just solely concentrating on that column all the way to the left, I would think, oh, there's a lift here. There's some sort of improvement with the new experience, right? But I can't really put a value there. And that's what the p-value helps with. So if I look all the way to the right column, I can see the p-value saying 0.07. So this is not statistically significant. Now I'm able to put a statistical value to this conversion lift I was seeing, and it's not statistically significant. But let's say I want to dive in deeper and understand a bit more about the effect size of the results I see, since I only know if it's statistically significant or not. So we're going to talk a bit about using credible intervals to assess effect size as a tool. So with credible intervals, you can better evaluate how the new experience you introduce compares to the performance of the control. So what I have right here is just here for examples of format that you will usually see a credible interval in. So you can see the one on the left, it has a peak, the posterior. When I say posterior is where the data is falling on the credible interval. So you can see that it has a peak in the center, but the one on the right is just a general horizontal line chart. You'll see both formats in practice, so I wanted to call out what they look like generally. You also may be asking or thinking to yourself, I've heard confidence interval, is that the same thing? The answer is yes. Credible intervals and confidence intervals are the same thing. It's more of a philosophical preference of the statistical approach you take. So you could be working with a data science or a data science team that uses confidence intervals versus credible intervals, but they're the same thing. So let's get back to what some of the benefits and why we should be using credible intervals. So some of the benefits: they can measure the magnitude of effect when performing your hypothesis test, and they measure the range of uncertainty, able to assess risk and confidence in the effect you're seeing. So awesome. Let's look at our experiment results as a credible interval now. So we're going to concentrate on the top chart. In the top chart, you can see that the lower end of the posterior of the data, that's on a 95% confidence, is negative 0.15. And you can see at the higher end, it's at 4.1. And then the center, you have the mean equals 2. So that's at the peak of the posterior. What that mean is correlating to is that lift we saw. So that 0.02% lift, that equals 2 on this credible interval. And this credible interval is showing annualized impact in the millions. So the higher end is actually 5.1 million is showing. And then the lower end would be negative 150K. So great, I can see where my data is placed on this credible interval. And I can also see that the lower end is going negative. So it's going past 0. And ultimately, when your credible interval goes past 0, it's automatically not statistically significant. So that's what's happening here. So let's look at the bottom chart now. I want to plot my p-value on this credible interval. So when I plot it, which is the vertical red line on the bottom chart, it's at 3.4%. So now I'm able to say to myself, all right, 3.4% of my data is falling below, is showing that it's falling below 0, so negative 150K. I'm also able to say now there's only a 3.4% chance that if I was to launch this new experience, that I would see a negative 150K, or that's the impact that this new experience would drive. What I can also now say is that there is a 96.6% chance that I would drive neutral impact, so even with the control, or up to the range of 4.1 million positive impact, since it's falling all the way on the opposite side at 3.4%. So because we know the results aren't statistically significant, we couldn't claim any of this as official impact due to the high probability it was just chance. But what we're doing here is exploring alternatives such as using a range, and it helps us to assess risk and magnitude of potential impact to make better decisions around the feature. So although this is an official impact because it's not statistically significant, we're still able to make different conclusions from it by looking on this credible interval. I'm now able to put my business expertise into this and understand what decisions I want to make now. So really what I'm asking myself here now that I've seen this data is the effect size I'm seeing meaningless or meaningful in a practical sense? So we're going to get a bit into practical significance here and what I'm referring to within this concept. So determining if an effect size is meaningless or very meaningful in a practical sense is applying outside knowledge of your area or business to your hypothesis testing methodology. So a credible interval is a methodology that will better help you tell the magnitude of your experiment effect size, but it will not tell you if the effect size that you're seeing is practically significant for your business. So you might be saying to yourself, why do I care if something is practically significant? Shouldn't I just care about statistical significance? But what if I told you statistical significance is not actual significance? So statistical significance does tell you the chance that the effect you're seeing is not by chance, right? So going back to that devil's advocate, the null hypothesis, telling you if you can reject it or not. The effect you're seeing is by chance or not. What practical significance is you applying your subject area knowledge and expertise to determine whether the effect you're seeing is meaningful in the real world to care about. So another big question you might be asking yourself, is there a tool I can use to help evaluate what is practically significant for my business? And there is a tool you can use, and it actually can help you determine practical significance more upfront, even before you launch your experiment. So we're going to talk a bit about minimum detectable effect, acronym MDE. So minimum detectable effect is a calculation that estimates the smallest improvement you're willing to be able to detect. In other words, you can ensure how long you will have to be able to run an experiment in order to detect something that would be meaningful to you. So some benefits of calculating minimum detectable effect can help you prioritize experiments based on time investment and projected return on investment, so ROI. And you guessed it, as I mentioned, it can help you determine what would be practically significant effects for your business. So let's talk about calculating minimum detectable effect. It consists of inputting 3 to 4 variables. So similar to the sample calculator we discussed earlier in this presentation, you're going to want to, the inputs you're going to want to use are daily amount of traffic of the site area you're going to experiment on, your baseline conversion of the site area you're going to be experimenting on, and the number of variants within the experiment. The catch is you do need 2 statistical parameters, and this is usually determined by your data science team. But I can promise you, if you were to try to talk to your data scientist or your data science partner, team, whatever it might be, they would be ecstatic to talk to you about this and to see how you can use it as a tool. And if it's worth your time to invest in something like this and incorporate it into your general practices. So say we applied a minimum detectable effect and use those inputs. So ultimately it can calculate the columns below and help you answer the following questions. I'm now able to answer, what are the effect sizes I care about? So I'm now able to see 1%, 2%, 3% lift, and what that revenue impact size would potentially be, and how long I have to run this experiment in order to detect the effect sizes I care about. So say I care about the 1% metric change here. I now know I have to run my test for 90 days, and the ROI I could potentially see is $1 million, or the effect size potentially see within that span of time be $1 million. So one of the challenges though with choosing minimum detectable effect is you'd have to get lucky to see smaller effects if you are choosing a larger MDE effect to power your experiment. So what I mean by that is if I chose 1%, I would have to, 1% metric change is the metric change I care about. I would have to get lucky in order to see a 0.5% or a 0.25% metric change because I'm powering my experiment for a 1% metric change. But really, minimum detectable effect could just be really beneficial with you prioritizing and understanding this upfront so you can make better decisions on what experiments you want to invest in. But now we're going to ask the question, what if my experiment turns out negative or in favor of the control? So This is what PMs do not want to happen ultimately when they're running experiments. They want to drive positives. They want to drive differences, significant differences and effects. But it's important that we talk about, since this will happen, how to really come out of this and understand the benefits of this. So I'm going to get into a bit of a mental model of experimenting to learn. So as a PM, it's easy to get caught up in running statistical significant experiments. That's really that's your goal when you're running experiments, right? That's what you care about. And that's fine. That's great. But this mental model of learning towards experiments is key to you getting the most out of the experiments you run. And when I say that, it's also worth noting that in order to get the most out of the experiments you run, you should be making sure you're setting up the correct tracking on your features that you're launching. So that could be either if your company uses segment tracking, if your company uses Google Analytics tracking, just making sure that you're setting up tracking so you can understand user behavior. So you have this tracking on user behavior, but then you're also running the experiment to understand its effect size. So you have these two pieces where you can learn a lot. So on that note, statistical significance helps you determine whether to pull a trigger on a new feature, right? But it's not the only thing to consider. So as I just noted, you have statistical significance, and you also have these other user engagement metrics now of how the user interacted with your feature, which is a whole other data set. So statistical significance is just one data point. But if you're setting up your experiment properly, you'll be able to track your user behavior, and that provides a bunch more data points where you can learn and create better strategy around your product as a whole. So really what I mean by that is, if you're setting up tracking and you're understanding how your user behaved with the feature, that could really change maybe even your roadmap, right? Because you're learning different things about how users are interacting with a feature that maybe you find is something you should be investing in sooner rather than later, and you change your roadmap, or you make a different decision. So all in all, what I'm getting at is to not just take statistical significance as the end all be all. You experiment to learn, and that's really key here. So this talk is called Common Mistakes when Starting A/B Testing. So to conclude, I want to touch on what are these 4 common mistakes that I went through examples within the presentation of what not to make and what you should be considering to do. So 1, only using categorical cutoff methodologies such as p-values to read an experiment. So as we went through, a p-value provides you a valuable data point. It provides you if your experiment is statistically significant or not. But it's really important to think about what do I care about further data and looking into further data around this. Do I want to look at the effect sizes? Ultimately, I think you should, regardless of if it's statistically significant or not statistically significant. And it could really help you just make better decisions around your feature. So number 2, not applying your business expertise to evaluate practical significance of effect sizes. So this idea of practical significance. So not using your focus area expertise and applying it to your feature. You really need to, once you can, have the tools to understand your data, now you need to apply your knowledge of what's the best decision I should make for my area or for my business based on what I know. And that would be applying practical significance and why it's important. Not using minimum detectable effect as an exercise prior to launching your experiment. Now, I'm not saying you should always use this tool. I do think it could be a very helpful tool, especially when you have competing priorities or if you're working with a smaller amount of resourcing. So maybe you only have X amount of engineers and X amount of time to implement an experiment. It can really help you set what your priorities should be with what you're concentrating on based on return on investment and based on how long you need to run the experiment for in order to see the effect you care about. And then finally, experiment to only look for significance and not to learn more about your feature that you introduce to your users. So again, this idea that statistical significance is the end all be all. It's not. You want to experiment to learn. You want to experiment to learn about your users and how you can better solve the user problems that they're encountering. So with that, thank you for listening. This topic is near and dear to my heart, so I hope I've taught you something, and I hope you found it helpful. And please reach out if you have any questions, but I appreciate you coming.